Section 4.2, Properties of Logarithms. The first thing we need to talk about are two specific types of logarithms that can be found on our calculators. The first one is called a common logarithm, and the second is called a natural logarithm. So our fancy schmancy calculators that you've gotten used to using here at school, the TI Inspires, will actually do any base of logarithm. And there's other calculators that will do that too. But most just general scientific calculators will only do what's called a base 10 logarithm or a base E logarithm. So let's learn a little bit about what those are, because those are the ones you can do with the calculator you're allowed for this class. So common logarithms are log base 10, but instead of writing log with a little 10 next to it, we just write the word log, and we don't write the 10. I mean, it's okay if you do, but typically it's just kind of a time saver for the common logarithm. And of course we call this the common logarithm. Okay, so that is going to be the log button on your calculator. It doesn't have a base. Now, natural logarithms are a log base E. So before we actually talk about how to write that, E is a naturally occurring number that's been labeled E for Euler, a famous mathematician. So it's kind of called Euler's number. And it is defined as the value of 1 plus 1 over some number m, use whatever variable we want, to the mth power, and that is as m approaches infinity. So as m becomes a bigger and bigger number that you're dividing here and putting the power of here, we get closer and closer to this value of e. So e is specifically used with exponential type of problems because it is an exponential by definition. So as that is calculated with m being a larger and larger number, we get an approximate value, which our calculator will give to us. We should be able to find the e button on the calculator, or like an e to the x or something like that. And somehow or another, you should be able to get your calculator to spit out a value of e for you. So it's approximately 2.71828818, blah, blah, blah. It keeps going. Anyway, that is the base of what we call a natural logarithm. Now, instead of writing an e next to our log base e, we actually write natural logarithm as ln. I usually like to use a cursive L because when I don't use a cursive L, it looks more like a 1. It can be mistaken for 1n when it's supposed to be ln. So that is our symbol that we use for natural log. You should be able to find a button like that on a scientific calculator as well. In fact, it's closely usually associated with the button that has E on it. Those are two different types of logarithms that we're going to see a lot as we go through this chapter. Alright, let's go ahead and just do a quick problem involving a common logarithm. So if you look at this formula they're giving us, it doesn't have any bases on our logarithms. That means the base is 10, and it's that common logarithm that we can just use in our calculator. The state of Utah has one of the fastest growing populations in the country, with an annual growth rate of about 2%. The number of years it takes for a population with the growth rate of r to double in size is y equals this formula. So this is specifically to double the size of a population, and it has to do with that 2 that's in the numerator. We'll learn more about that later in this chapter. Anyway, so it's log base 10, 2. We don't need to say the 10. Log 2 divided by the log of 1 plus the rate as a decimal. So this is a percent. The decimal would be 0.02, so we would have to add that to our 1.02. At the current rate, how many years will it take for the population of Utah to double in size? If the growth rate is smaller than that, like 1.5% instead, how many years will it take for the population to double in size? So let's just compare these two different results, and all we're going to do is use a calculator to calculate a common logarithm. So at 2%, we're just going to take log of 2, and then we're going to divide by the log of, remember we're using this formula, 1 plus 0.02, so 1.02. So that would be a 2% growth rate. Throw that on a calculator, you should get an easy peasy answer of approximately 35 years. Well, what if our growth rate slows to a 1.5% rate instead? Then how long will it take the population to double? So log 2 divided by the log of, this time our rate's going to change to 1.015 because 1.5% instead of 2% is that r that's being tacked on at the end there. So then if you throw that in a calculator, it equates to approximately 46.5 years. I'd encourage you to use whatever calculator you're used to using, that you're going to be using on tests and things like that, and try just doing those problems in your calculator and make sure you can get them correct. Alright, here's just a splash of important logarithm properties. I decided to kind of put them all up front. We're going to be exploring them in this section. We've got exponents 0 and 1, so remember a logarithm is an exponent, so when you have an exponent of 0, your value is always 1, and if you have an exponent of 1, the value always stays the same. So that's where those logarithm properties come from. We're going to look at those along the line. We're going to look at the product rule and the quotient rule and the power rule, the change of base formula that allows us to change any base logarithm to that base 10 or base e so we can solve it with a calculator. And then we have our one-to-one property that we learned in section 4.1. That's going to be handy when we solve things, because if we have a problem without logarithms, we can put a log on each side and it still is equivalent. Or if we have a problem with logarithms on each side, we can actually get rid of that and just solve what's left. So that will be powerful for solving. One thing to just remind you of, based on the domain that we talked about last time, is that you cannot take the log of a negative number. Logs of negative numbers are not defined. So your calculator won't do it, and you shouldn't either. And in fact, we should be careful to check to make sure that solutions are not going to cause us to take the log of a negative number.